So we're going to start a series of lectures on scientific computing. Scientific computing is one of the most important tools sort of the last several decades, where we have the ability to simulate systems at scale and to build very sophisticated models of physical processes, all by running them on computational engines, which model a set of physics principles and constraints. And so it's kind of transformed what engineering design is able to do in building in a virtual world. And many of our top engineering applications, like building an airplane or a car, are often designed first through computational engines, through methods of scientific computing, before we actually build them in a real instance. So what we want to talk about are those kind of methods available to us for traditional scientific computing. In other words, forward solving of governing equations, let's say, of a given physical system. So a lot of what we want to start with is just this very simple concept of numerical differentiation. If you look at the history of what we've done mathematically, most of the world was expressed in geometry or in terms of geometry all the way until the time of Newton, in which we developed this idea of the derivative, or calculus. And calculus allowed us to express rates of change of different quantities. And what essentially we were able to do then is to start writing down a lot of our physics-based models as relationship among derivatives, both in time and in space. This includes things like Maxwell's equations for modeling out electrodynamics, or quantum mechanics, which you have the Schrodinger equation, Navier-Stokes to model fluid flows. All of these models across physics are basically ways in which we represent how things change in time and space through some partial differential equation or differential equation. So the first thing we have to understand is that when we come into scientific computing, we are going to have to find ways to compute derivatives. So we're going to start off this section with numerical differentiation and talk about some of the techniques available to us for computing what a derivative is. Okay, and remember, the derivative is just the rate of change of something. So let's start off then talking about derivatives. So we're going to come back to the idea of a derivative. So this is the formal definition of the derivative that you would get in the first few days of calculus. df dt, so the rate of change of f in time. And calculus, this is the big step that Newton took. Like if you take something infinitesimally small, divided by something infinitesimally small, how do you make sense of that? Normally when you divide by 0, that's a bad idea. So the bottom is going to 0, the top is going to 0. What do you do with a quantity that is 0 over 0? And what calculus allowed us to do is to formally define that limiting process. So in other words, as you take, here's the actual definition, you take delta t goes to 0 of the difference of the function at f of t plus delta t minus f of t divided by delta t. So on the top, as delta t goes to 0, you get f of t minus f of t, which is 0. And on the bottom, as delta t goes to 0, that goes to 0. And so what calculus allows us to do is make sense of this fractional relationship. And in fact, in many ways, what we really think about when we do numerical computations is undoing calculus. So we're never going to take the limit as delta t goes to 0. We're just going to simply work with this expression here and make delta t small. So if I want to compute a derivative, which is essentially a slope, then all I do is take a rise over a run. But then I'm here taking the rise over the run with delta t to be small. And of course, this is a time derivative, but we're going to use this also to compute spatial derivatives or any kind of derivative in general that we want to be able to evaluate. All the derivative is always doing is evaluating for us a rate of change of something. And in physics and engineering, that's often the main thing that we want to do is start looking at a system, see how it's either changing spatially or changing in time or changing both space and time. And that is all going to be given by relationships of how derivatives are integrating or talking to each other. So this is going to be the basic framework. The basic framework being I'm not going to take infinitesimals. I'm going to take some kind of formula like this, which is an actual difference formula, and compute the derivative directly. So again, just a reminder, this is just a rise over run formula. And we learned this even in high school about how to do things like rates of change. You know, average, if you take the average velocity, it's something like a rise over run formula. And so we want to be able to do this now in a principled way with the ability to compute errors. So that's the big question then, is if we actually have these slope formulas, what we really have to evaluate is how do we compute the error and how much error can we tolerate? And so what we're going to come up with is a bunch of strategies for how do we compute derivatives and how much error do we incur in computing the derivatives in these different ways. There are a lot of ways to compute derivatives. And in fact, one of the things I'll say here is that we're going to learn some very basic techniques, but if you have noisy data, what I'm telling you here in terms of some of the methods we use may not be appropriate. Numerical differentiation, especially for noisy data, is exceedingly hard to get good derivative estimates. So you should keep that in mind. Even though it's one of the most basic things we do, which is to compute a derivative, it's actually a very difficult task in general unless you have really clean data, which is very rare except for in, let's say, numerically generated data. So we're going to start off with this idea of a Taylor series. Everything we do in numerical differentiation is going to be based upon Taylor series expansions. In particular, here's a Taylor series expansion of f, the function f, at t plus delta t. So just a little bit off of t. And Taylor series, what you learn is you can expand this around t, which is equal to f of t plus delta t df dt. Here's the derivative. And we can expand this out. In fact, we're going to truncate this exactly at delta t cubed here. So we do this approximation. It's exact. So this formula here is exact, except for I don't know what this coefficient C1 is. Okay? But the proof that you can actually say this is exactly the representation of f at t plus delta t, sort of in some sense contextualized around f of t, which relates and has its derivative estimates here. This is one of the things that we learned early in calculus, and in many ways, numerical computations, if you want to be understanding what most scientific computing does, the Taylor series expansion is probably one of the most important tools you have to understand or know about. By the way, I can also do this Taylor series expansion about f of t minus delta t, which is the second expression here. So again, it's given in terms of f of t. Now minus the delta t, first derivative, plus delta t squared, second derivative. And then again, a truncation up here, which is the minus delta t cubed, plus a term where the thing I don't know there is actually the C2. So the C2 is the constant that goes at the end of here, but again, an exact expression that you would have here. Now the important thing is that the constant C1 lives somewhere between t and t plus delta t, and the constant C2 lives between t and t minus delta t. So everything here is exact. And so I've done nothing yet to get ourselves to a point to estimate a derivative. Except now with these two different formulas, which are exact, I'm going to do something with them. What I'm going to do with them is I'm going to take the first formula here, and I'm going to subtract from it the second formula here. So this is a subtraction of these two exact expressions. So let's talk about what this is going to do for us. So we're going to first have this term here, f of t plus delta t, subtracted from f of t minus delta t. But on this side, notice what's happening. I have f of t subtracted from f of t. These two are going to cancel. Then I have this expression subtracted, but this is already a minus, so I'm going to get two of these. And then these two are also going to cancel. So at the net effect is at the end of the day, you have this expression here. So it says that the f of t plus delta t, f of t minus delta t is equal to delta t times the first derivative, the factor of 2, and this other expression here, which has a delta t cubed in front. Now this is going to be important because what we're going to do is take delta t to be small. So if you have delta t being something like 10 to the minus 2, then delta t cubed is like 10 to the minus 6. So what we're going to do is treat that as the error term in the approximation for the derivative. In fact, what I can do is take this expression here, and from this expression, solve for the first derivative, which is sitting right there. So I can move everything to the other side, and what I'm going to get now is this expression right here. So this expression tells us that the derivative is equal to, this is our slope formula, right? This is one of the points, f of t plus delta t, f of t minus delta t. This is rise over run. This is nothing more than our slope formula that we learned for approximating a derivative, okay? But what else is here, and again, this is an exact expression, is this term here, which has a delta t cubed in front of it, times the third derivative, but now I've replaced the constant c1 and c2 by some other constant c. So there is some value there of c where it makes this hold explicitly. I don't really know or care to know what the value of c is. All I know is that it exists. And so now what we're going to do then is say, okay, but I'm actually going to throw away this term because this term here has a delta t squared in front of it. So it's much smaller than this term. Okay, that's the idea, provided that the third derivative is, in fact, order 1 or something like this. So the error estimate is that I'm throwing away something that's order delta t squared. In other words, this order symbol means it's about the size of. Since I have a delta t squared here, I assume the other coefficients are order 1. In other words, there's some value, but they're not big or small. They're just, some constants. And then the order delta t squared is the scaling of that term as a function as I make delta t smaller and smaller and smaller. So if I cut delta t in half, right, then this term here is 4 times smaller. And so one way to think about it is I can control the error in my derivative estimate by making my delta t smaller and smaller and smaller. Again, I cut the delta t in half, the error goes down by a factor of 4. So this is the simplest formula possible for computing a derivative. Okay? It's called a finite difference method. And the finite difference is everything's chopped up into slices of thickness delta t. So that is my interval. And so finite differences, the differences between these are separated by 2 delta t, and it's divided by 2 delta t there. So that's how I'm going to actually produce derivative estimates. Okay, so let's go back to this concept, right? So the derivative is just a slope. It's the rise over the run. Oop. Let's see here. Okay, all right. And so now what we can do is proceed further with this idea of the slope and start thinking about computing higher derivatives. So let's go back to this expression here. I'm now going to continue my Taylor series expansion, which is f of t plus delta t, okay, is equal to, here is the Taylor series expansion, but now I'm going to take it all the way up to delta t to the 5th. So what I'm going to show you is my slope approximation can get more and more accurate by changing the formula for how I'm computing the slope. Here's the Taylor series expansion of f of t minus delta t, also expanded all the way to delta t to the 5th, which is has a 5th derivative in front of it. So all I did from previously, that was different from previously, is that I expanded and kept more terms in my Taylor series expansion. So the question is, what does that allow me to do? Well, what allows me to do now is to start thinking about, I can subtract these now, okay? And when I subtract these, notice what I'm getting here. I subtract these, I get, again, the first derivative. Remember, the function itself, f of t, cancels with the f of t. The second derivative cancels with the second derivative. And I get this expression here that goes up to delta t to the 5th, okay? And I can use this here, this expression, to write this out here with now I'm pushing all the error. I'm going to throw this term away here. You see the C1 and C2 here, but this is a Taylor series expansion for the difference of f of t plus delta t and f of t minus delta t. Now, I could change this same formula around, so wherever I see a delta t, I could change it to 2 delta t. In other words, instead of having sliced my interval up in delta t's, I could have done an interval of 2 delta t. The finite difference now that I'm looking at is twice as big. And all I have to do up here is replace the delta t by 2 delta t, and here's a second formula. F of t plus 2 delta t, f of t minus 2 delta t. Here's the expression I would get from this. So I'm just basically thinking about the finite differences with delta t and 2 delta t. The question is, why would I do this? Because I now have two expressions that are available to me, okay? But here's what I'm going to do with it now. I'm going to take the second expression and subtract it from the first expression, okay? Now, the reason I'm going to do this is what you'll notice here is when I do this, I have 2 of these, 4 of these, and now I can actually decide to do this so that why don't I choose to cancel out these 2 terms here. So in other words, I could actually take the top expression. There's a 2 in front of this one, a 16 in front of this. What if I took 8 of these equations, so multiply the whole thing by 8, then subtracted it? If I did that, the third derivative term would now vanish. So now I have 8 of these, just this one here to subtract. And what ends up happening then when you do this is that you get the following expression. I have a new expression for the derivative, which is the derivative is now one term, which is minus f of t plus 2 delta t, 8 f of t plus delta t, and the 8 comes from the fact that I multiply this by 8, minus 8 f t minus delta t, and then f of t 2 minus delta t. So it's a little different expression, 12 delta t in the bottom, but here is the big win that just happened for us. Because I got rid of the third derivative, I've pushed all of the error up into a term that has a delta t to the 4th in front of it. So now if I cut delta t in half, my error, instead of going down by a factor of 4, the error goes down now by a factor of 16. So what I've done now is used a more sophisticated slope formula, which doesn't just use 2 neighbors to compute slopes. It uses 4 neighboring points to compute the slope. And by doing so, I can push the error down by another 2 delta t squared. So this is how you would actually start playing games with computing derivatives. This is a more accurate derivative estimate using the same delta t's that I was using before. So if you have a set of points and you want to take the derivative of it, and the points are coming in delta t increments, you could do the simple rise over run formula we had previously, or you can use this one here, which gives you an improved error estimate for the first derivative. And of course, if you use more neighboring points, so instead of just using my current neighbors and their neighbors, so that's the delta t's away from you, the 2 delta t's, I could use 3 delta t's away from you, and you could even push that down to delta t to the 6th. These are different slope formulas, all of which try to compute that derivative more and more accurately, okay? So this is something that people have worked on for decades, is how do I improve my estimates of derivatives? This is how it's fundamentally done, is you're basically using either more neighbors. There are different numerical differentiation techniques such as spectral methods based on Fourier transforms, but here we're going to just talk about finite differences, which is here. Okay. So we could also just approach this, we also want to do this, what we did is we subtracted these 2 Taylor series. This is how we got the rise over run estimate. We could instead have added the 2 formulas, and if you go back to our first expansion and you add them, what ends up happening is when we subtracted them, the function f and a second derivative fell out. When we add them together, the first derivative falls out, and what we end up with is the function and also the second derivative. And what you end up with is this formula for the second derivative. So I subtracted them to get the first derivative. I add them to get an estimate of the second derivative. And what the second derivative estimate says is it says the second derivative is f of t plus delta t minus 2f of t and f of t minus delta t. So I use 3 points, so myself and 2 neighbors, to compute the second derivative at that point. One thing of note, on the bottom, you have delta t squared. So this is important because now, as delta t gets smaller and smaller, this is now, instead of a delta t on the bottom, is delta t squared. And the error here is order delta t squared in this first approximation, where what you're doing is adding these two Taylor series expansions that you would have. So this is kind of the basic framework for building derivative estimates. And in fact, these are sort of very well established, right? So computing derivatives was one of the first things we ever did when we developed computers for scientific computing applications. What we were interested in is solving physics-based problems, which means we had to compute derivatives. And so we've had these things like these tables around for quite a long time, which is what you're looking at here. These are what are called the order delta t squared center difference formulas. And the center difference formulas use neighbors equally on each side. Okay, so I have a neighbor on each side or 2 neighbors on each side. And what we're doing here, this chart shows us how to compute the first derivative, the second derivative, the third derivative, and the fourth derivative. These are well-established formulas, and the truncation I have on each is order delta t squared. Okay, so we have these formulas that are actually fairly easy to write a program to solve. And so there they are. You should always have these in your mind. And of course, you can easily use these simple formulas to get sort of a first approximation of data. And we'll also use these later in scientific computing applications where we're solving partial differential equations. We'll want to estimate the derivatives of our governing equations with these kind of formulas. We can improve them, however. So delta t squared in numerical parlance isn't that accurate, actually, right? What you'd really like sometimes is something that's much more accurate estimation of a derivative. And so here, what I have for you is the order delta t to the fourth center difference formulas. The big difference between them is that you use more neighbors. That's it. So the formulas can be derived in the same way. Taylor series expansions, add and subtract, but now for these higher derivative estimates, the more accurate you want a solution with finite differences, the more neighbors you're going to need. And that's all this highlights for you. So even a first derivative here, now what you have is 2 neighbors on both sides, whereas if you had this delta t squared, it's only 1 neighbor on a side. And you can start seeing I've got more terms here. A second derivative estimate, I have more terms than what I'd have here in the instead of using 3 points, I'm using 5 now, and so forth. So you're just adding 1 point on each side, and you drop the error down by another delta t squared, going from here to here. And if you want order delta t to the 6th, well, then you'd have to use 2 more neighbors on each, 1 more neighbor on each side, and then you'd get some new formulas here for those. So a lot of it depends on what your needs are for accuracy, but these here are fairly simple to write and program, and they allow you a pathway towards being able to compute this very important quantity that we call the derivative. And notice, all these are fancy slope formulas. Slope formulas where the delta t is fixed. So in other words, we're not even really doing calculus anymore. We're doing the inverse of calculus. Instead of calculus, where we take delta t and taking the limit as goes to 0, what we're saying is I have a derivative, which is technically where the limit of delta t went to 0. I'm backing that up to a finite size delta t and computing these slope formulas that I would have here. By the way, there's one other set here that's on the table, and so this set of tables is really important to have handy. But this is what are called forward and backward difference formulas. So suppose on an interval, I'm on the end. I have no neighbor on my left. How do I compute a derivative? Well, you can still use Taylor series expansions, but now instead of using your neighbors left and right, center differencing, you use instead two neighbors on the right. And you can derive, just through Taylor series expansions, adding and subtracting in the right way, the following formulas, which are the forward and backward difference formulas, delta t squared accurate, for the first and second derivative on the ends. So this is how you take care of the interior domain of where you're going to differentiate. At the edges, you would use these kind of formulas here to compute an estimate of the derivative. So this is a really simple introduction, right? And in some sense, from the very first day of calculus, we learned this concept that the derivative, right, is essentially a slope, a way to estimate the slope. And what I've shown you here is we're just taking Taylor series expansions and using them in smart ways to compute slope estimates or derivative estimates where we can actually bound the error. And so these become foundational for scientific computing because typically we're representing all of our physics-based models in terms of governing equations that are basically expressions of how derivatives are relating to each other to prescribe the physics.